So we're here at the SID Display Week here at the iZone. And hi, so who are you?
Hi, I'm Marta. I'm the PR for the XTPL company, and we are very happy that we won honorary award at the iZone. Let me introduce you to Philippe Granek, the inventor of our technology for printing ultra-precise light conductive lines.
So hi.
Hello, hi, I'm Philippe with XTPL. Really happy about being here in Los Angeles, and maybe I can explain you what XTPL does. XTPL provides a technology for printing extremely fine structures using nanomaterials. We have developed a special unit for printing. We call it a printing head, XTPL printing head. It's a uniquely designed printing unit and electrical controls that control the position of the ink. We like to say that this control of the deposition of the ink is like playing music to nanoparticles. We play the music, they start to dance, and by dancing they form very, very fine structures that are impossible to be printed with standard printing technologies like screen printing, inkjet printing. So it gives you a lot of value when you go to very fine structures for manufacturing of parts of displays or various types of printed electronic devices.
Because this looks like it's very small. What are you talking about? Nano?
So this is, let's say, about 100 times more thinner than the human hair. So that's about half micrometer.
And why do you show this here? Are you printing that small?
Yeah, we're printing that small, and that's the whole thing here, that you can be printing in additive manufacturing even at the sub-micrometer resolution, so you can go below single micrometer. Ideally, we print a few micron lines, but you can go even to below 100 nanometers potentially, and this is not possible with any other existing printing method in the world.
Where you show this flexible display here, is it something to do with that?
Yeah, so we can print structures also on flexible substrates. So our structures that we print can be also flexible, and like I said, this can work on glass, on foils, and you can print various materials, metallic conductive structures, but also quantum dots and semiconducting materials at very high resolution.
So when you talk about the dance, what does that mean? Does it mean there's some kind of swing happening?
Yeah. So I don't know if this is probably could be helpful. So you see the ink here. It's a wet droplet of the ink with individual nanoparticles inside, the small dots, and then we make them move together to make a very narrow structure, because the electrical field forces them to move like this, and the control of the electric field is what I call this music that makes the nanoparticles move. And this move is, like I said, can be called a dance within the liquid surface, and then afterwards we dry the liquid and the solid structure stays on the surface, and it can be used as electrical connector or whatever purpose you want it to be used for.
So right here, what is this that's showing here? Is it an example of what would be printed?
No, this is actually a structure that is better seen with the microscope, but there are very tiny wires between these electrical pads, and some of the wires are broken, and we are repairing them. We are healing this broken structure by applying our additive manufacturing, and it's like a good example of our application for open defect repair. If you have like a bad pixel and not working pixel in your display, before you ship it to your customers, you want to repair this pixel by healing some of these broken lines.
So this is like a repairing machine.
It's like one of the, let's say, application fields is to do repairs. Obviously, we are hungry for other applications as well, but this is a good application where our company can already provide value today.
Can you fix dead pixels?
We can fix some classes of dead pixels, some classes of defects.
What kind of display, like LCD or OLED?
For OLED, for LCDs, and the particular class is called open defects, where you have a line that is broken, that is not electrically conductive anymore. So you come with a small metallic patch, you close the line, it's electrically conductive again, it's very fine, and it activates the pixel again.
So maybe we can sit back down. So why did you win the prize right here at the iZone? Like,
sorry?
Why is this so important?
Well, I think the application of additive manufacturing of printing technologies at this very fine resolution can be potentially interesting not just for the defect repair in the displays, but also to deposit other classes of materials like quantum dots for light emission at very high precision. And we hope, and we had a lot of discussions with potential partners these days, that this will be a growing business for us.
But the way that quantum dot displays are going to be made, right? They're going to be made like in huge fabs that just print like huge things, right?
So,
but where's your space in that market?
Well,
because you're just making small things, right?
We're making small things, and today we're making them with a single printing unit. So we are in the process of scaling the printing unit, so you will have multiple printing heads joined together, so then you can print faster on the large surfaces, and this way, you know, we will get it to transition to work on larger surfaces and to the more industrial applications where speed and throughput is of essence.
So you would print large surfaces of what? Like the whole display?
You know, elements of display, depending if this should be, you know, parts of electrical circuitry, part of electrical conductive structures are very fine, or depositing light emitting quantum dots locally. So this is, you know, where we have just initial discussions here. Hopefully some of them will convert to projects.
So you kind of discussions with what kind of companies?
Equipment manufacturers that will work on supplying, you know, final equipment to display industry. They would be interested in integrating our printing unit in their machines, and the end users being the touchscreen manufacturers and the display manufacturers who are just interested to understand, you know, how our technology can fit into their technology roadmaps and how we could think of potential future developments, not for this particular generation of the product, but maybe for N+ and 2 future generations where this technology can play a role.
So what's your background? Where are you based?
We are in Europe, actually, in Poland, in a city called Wrocław, a really interesting place with a lot of universities. So we have a lot of well-educated people there. Our labs are filled with smart people, you know, coming from chemistry background, mechanical engineering, electrical engineering, physics, even mathematics, and you know, software experts. So it's a good mixture of people that we can get there. We don't have to compete against you know, companies like companies in Silicon Valley. So we have you know, maybe easier access to talents there. But we are also establishing a footprint now in Bay Area because of the potential customer base is not really in Poland for us. It's rather US and Asian markets that are interesting for us, so we will be present here as well.
And how many people?
We are now 35 people back in Poland and establishing a small group here in US as well.
And what do they all do? What's the roles of all these people?
Well, they work like on electrical systems here to, you know, to design the electrical circuitry, to design the software that drives the head, the mechanical part, so the mechanical components, the chemistry of the inks, so the particular inks that are being used to print nanomaterials. This is the chemists that work on that.
What inks do you have there?
These are the examples of silver inks that can help us print electrically conductive structures like silver inks, but we do also work on other metallic structures that can be printed. We like to show that our printing head comes with some starting kits of materials that you can start printing right away. But if people are interested in, you know, using their own inks, we are also open for that and try to help them optimize their ink for this particular printing unit.
But is this like a prototype, or is this already fully working?
Yeah, so for the defect repair, so the initial niche that we are aiming at display manufacturing, this is a working solution, and we are now in process of integrating that into the tools of equipment manufacturers who are at the end of the day supplying equipment to the module manufacturers, the display modules or touchscreen modules.
Because one of the problems with the display industry is this yield problem, and then there's so many displays that just get thrown in the trash.
Yeah, I mean,
as
you're pushing the limits of resolution and getting finer and finer pitch sizes, automatically some of the structures will have defects, and some of the defects makes sense to repair them. And, you know, if you have a tool that can improve your yield a little bit, then this is where we can come into play and make people happy.
Would there be some kind of system with cameras that can detect where the thing could be going in and repairing?
We think there are already pretty good systems for defect detection and defect qualification out there. We don't want to go there. We want to be the guys who, you know, after the defect is classified and detected, we are the ones to repair it, right?
So maybe Radiant, the camera from Radiant is one of those, and they identify, and then you go and fix it, maybe.
Yeah. So usually I would expect this is like a two-step process. First, you look for the defects, you classify them, and then some defects can be repaired with this method, some defects can be repaired with that method, some defects cannot be repaired, so you need to discard the whole module probably. So, and we would be one of the repair methods that is good for open defect repair, not for the short circuits. If you have a short circuit defect, then it's really good to use lasers just to ablate the defect our technology would not bring advantage there. But for the open defect, having the possibility to deposit very fine structures in a fast and easy way, this is, I think, where the processing time and the costs of such a repair is of advantage in our case.